Okay, I hope people can see that. Let me know if you can't. So yeah, the talk's on some work we did in this paper here at the end of last year with Teresa Abel, who's Arthur's student, and Arthur Lipstein in Durham. And it's entitled Towards Virasoro-Shapiro and AdS5xS5. So the idea is to use some of the recent bootstrap techniques on the conformal field theory side and use them to try and understand what's going on more on the AdS side, or in particular, try and see if one can rewrite things and have a look a bit at the structure of amplitudes and the AdS side of things. So here's a kind of a very, very quick picture of what's going on. So there's been a lot of progress in the last, well, number of years, but maybe 4 or 5 years in particular. In AdS-CFT, and I'll be focusing on the canonical classical AdS-CFT, so n equals 4 Yang-Mills and 2B string theory on AdS5xS5. So traditionally, since this is a weak strong coupling, you would imagine the flow of information would be that you do calculations in weak coupling, in gravity on AdS side, and that would give you information about the CFT in strong coupling. But as you probably know, more recently, because of bootstrappy techniques that have come to the fore in conformal field theory, and are particularly nice, actually holographically, because the spectrum simplifies so much. The information has kind of gone in reverse, really. So people have been able to bootstrap results at strong coupling and conformal field theory with very little reference to the AdS side, and therefore obtain predictions for what we should get on the AdS side. And now this talk now is a little bit different again, I suppose. So I want to use some results here and use some insight from them to have another look at the AdS side and see if we can learn something, and in particular, write things in a nicer way with more structure, more of the 10-dimensional symmetry. So specifically then, I'm going to be looking at tree-level string corrections here, which have recently been bootstrapped in a number of papers. I want to use some of these results and get some insight from there. And I also want to have a look at some results from a couple of years ago on tree-level supergravity, which Simon Karan-Huot and Trin found to have a hidden 10-dimensional conformal symmetry there. So I want to see if we can sort of get some insights from these two recent results. And what we'll find is, that the 10D structure for the conformal correlators found for the tree-level supergravity kind of is maintained, if you like, that there's a well-defined way of packaging together, if you like, many correlators into one object, which has a sort of 10-dimensional structure. And so that's on the conformal field theory side. And on the AdS5xS5 side, we'll also see that there's a much nicer way of discussing things there. So, you know, you don't have to discuss all the component fields separately. One can actually package everything together into a scalar superpotential. When I say everything, I'm very much focused, by the way, on 4-point amplitudes here. So, you know, I'll comment a bit about generalizations, but at the moment it's just 4-point interactions. Okay, so I'll begin with an outline. I'll review some basics, but please sort of hurry me up if I'm being too slow. So I'll do basic AdS-CFT just with scalars in AdS space, but it'll help us to remind us of a few things there. Then I'll talk about the actual theory we're interested in, namely 2B supergravity or 2B string theory and n equals 4 super Yang-Mills. And then I'll talk about how to kind of mimic, if you like, some of the scalars in AdS space, but to do the full calculation AdS times S and conformal field theory. And I guess what maybe one of the outputs of this is that there does seem to be a well-defined scalar effective potential on AdS5 cross S5. So I'll kind of try and introduce the details first and get slowly more technical. So then I'll later introduce some more technical details about covariant derivatives. I'll define Melon amplitudes, and then I'll get to the end. And oh, I will go back to supergravity. So a slightly strange feature of this is that although we're inspired by this 10-dimensional structure for supergravity, I will be explicitly excluding supergravity from what I'm talking about mostly. So I'll then go back and discuss a little bit about supergravity at the end. Okay. I should say, please feel free to interrupt at any point and ask questions. I'm very happy to be interrupted. Okay, so basics of AdS-CFT. Well, I imagine everybody knows this to some degree. So we have states on the AdS side. They're dual to operators in a conformal field theory. In particular, a scalar field with a certain mass given by this is dual to a scalar operator with dimension delta. Okay, and then amplitudes on the AdS side. So amplitudes of any number of these fields or states in the AdS are then dual to correlation functions in the conformal field theory side. So in particular, we might have some sort of theory. Let's just have scalars, or let's just consider scalars for the moment. And you've got some sort of phi to the 4 term in an effective action on the AdS side. And I'll be slightly more general and more relevant to what I'm doing. Let's have 4 different scalars with possibly different masses. So we have some interaction. I'm thinking, well, okay, most of this could be in any dimension, but I'm thinking of AdS5. So we have some action d5 of x hat. So it's over that's over the AdS5 space, and we have the phi to the 4 interaction. Okay, and what do we do with that? Well, we convert that into a Witten diagram, just in the same way as you would in quantum field theory. You take phi to the 4 interaction, and you can from it compute a tree level 4-point amplitude. Almost exactly the same thing takes place here, but instead of a Feynman diagram, you have a Witten diagram, and the Witten diagram goes from the boundary of AdS5, which is a 4-dimensional Minkowski space, and explicitly what happens is this object here, this interaction, essentially gets replaced by this integral. So effectively, you just end up replacing your scalars with bulk to boundary propagators. And that gives you then a simple integral. This is an integral over x hat. It depends on x1, x2, x3, x4, which are points in Minkowski space. I'll say a bit more about this bulk to boundary propagator, but I'm using an embedding space formalism, which I'll introduce shortly. But the basic point is that this is a simple 5-dimensional integral of something depending on x1, x2, x3, x4. So you get out a function of x1, x2, x3, x4. And that function that you get out is the corresponding correlation function of the operators dual to phi in the CFT. Okay, and these particular functions have become known as D functions. In this case, it would be D delta 1, delta 2, delta 3, delta 4. Okay, so this object here I've called the bulk to boundary propagator. So it has this very nice simple form if we use the embedding space formalism. Otherwise, it's just slightly more complicated looking. So the embedding space formalism, if again specific to AdS5 and Minkowski space 4, both of these live in a 6-dimensional space with a metric which is minus, minus, plus, 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 or possibly the other way around. And AdS space then is the subspace of this 6-dimensional space satisfying that equation, where the dot corresponds to a contraction with the eta. Whereas Minkowski space is the subspace that satisfies this equation. But this equation here is conformally invariant. I could scale the x's as well. So you also take out a scale and therefore reduce it down to 4 dimensions. Okay, so that's a very quick introduction to basic AdS-CFT that I need. So I'll need these D functions basically. Now, recently it's been useful, very useful to consider Melon transforms of functions in the CFT context. So very briefly, in this case, this D function, D delta 1, delta 2, delta 3, delta 4, has the following representation. So here I integrate over delta ij. Delta ij are symmetric in I and j, and delta ii is 0, and I and j run from 1 to 4. So there are therefore 6 independent delta ij's, and they also satisfy this equation. And there are 4 equations there. So there are 2 independent delta ij's, and these very closely mimic kinematics of momenta in any dimension, I guess. So we tend to call delta 1, 2s and delta 1, 4t and delta 1, 3u, and there's an equation between st and u. Okay, so in case you're familiar with these Melon transform in terms of s and t, then this is just the same thing once you plug in these values. And there's a contour integral which we don't need to go into. Okay, but this D function then is given by this integral without any m there. It's just given by that integral. And the interpretation of this is then that we define a Melon amplitude of any function. So it replace the left-hand side with an arbitrary function and replace the right-hand side with m, a function of s and t, or delta ij if you prefer. And that m would be the corresponding Melon amplitude for the function. So in this case, the Melon amplitude is just 1 because the integral is there without the m. So m is 1. Okay, and we see that the Melon amplitude is somehow the analog, if you like, of the momentum, the usual momentum space amplitudes. So again, for 5 to the 4 theory, you would have a corresponding, the corresponding 4-point amplitude would really be 1, or just the coupling. And the Melon amplitude is also just 1. And this analog of flat space amplitudes is made a bit more precise because actually you can reproduce flat space amplitudes from the holographic Melon amplitude by taking a large S, large T limit. Okay, so that's 5 to the 4. That's probably very well known to most of you. What about derivative interactions? Okay, so derivative interactions. So I'm on AdS5 space. So I could, for example, have the following sort of derivative interaction. So the nabla here are just some AdS5 covariant derivatives. I need to contract away the indices, so let me just contract them pairwise like that. So that could be some sort of interaction that one might expect in some field theory on AdS5 space. And that then, so now you have to do a bit of a calculation, and actually I'll show you how to do these sorts of calculations explicitly a bit later. But the result of doing the calculation is, so what do? I just replace my phi's with my bulk to boundary propagators, and I end up with some integral again, and the derivatives then just give me a slightly more complicated integrand. So I just have a simple integral over d5x hat. And in fact, you can rearrange it so that it's again of the form of a D function, but with some higher values here. And also you might have to multiply by some x squareds. Okay, and then in this case, you can then convert that into Melon space. So namely, plug that and replace this here with that and look at the resulting M, which makes this equation make sense. And you'll find that you'll end up with a quadratic Melon amplitude. Okay, and again, you see this relation that the number of derivatives. So, you know, if you were just doing quantum field theory, you could be studying an undergrad or MSc student. What's the corresponding amplitude for interaction with derivatives, and they would end up with some s squared plus t squared plus u squared. The same thing is true in Melon space, except that there are some dots here, so there may be some lower order terms, some STU terms, or a constant term. Okay, and that's corresponding to the fact that actually it's the large S, large T limit where the correspondence with flat space amplitudes really is precise. Okay, but anyway, a two-gauge derivative interaction corresponds to a degree K polynomial, Melon amplitude. Okay, so that's the sort of general introduction. Now I'll go to more on the specific theory we're looking at. So we're looking at 2B string theory and its relation to n equals 4 Yang-Mills. So we have parameters G string and alpha prime on the string theory side. And we have a coupling, G Yang-Mills, and N, SUN, because we consider a family of Super Yang-Mills theories, or a family of gauge groups. And these are related via AdS5xS5 in the following way. Okay, and in actual fact, so I'll come back to G string and alpha prime later, but we tend to think of this as the expansion. We expand in G Newton, sort of gravity expansion parameter, G Newton, which is 1 over n squared. And then we think of the string excitations as being excitations in alpha prime. Okay, and then very quickly, 2B supergravity and n equals 4 Yang-Mills. So I mean, the only thing I really want to say is that there's a lot of stuff going on here. It's complicated. Okay, so supergravity has dilaton, axion, graviton, various p-form field strengths, including self-dual 5 form, and then it has fermions. So there's a lot of matter there, all living in 10 dimensions. However, if you linearize it on flat superspace, then it can all be packaged together into a single chiral superfield. Okay, and that roughly speak, well, I've just given you two terms of it really, but it starts off with a dilaton axion. It goes up to theta to the 4, and the theta to the 4 term contains the Riemann tensor as well as the 5 form field strength. And then there are no new components beyond that. It actually satisfies a reality condition at 4th order like that. Okay, so you might hope that if you want to try and simplify things, you might hope to try and make use of such a thing. But this is only true on flat superspace, although actually a similar thing is true on AdS5xS5. Obviously, if we're doing string theory, then there are also massive string states. All I've described here is the supergravity states. Then on n equals 4 super Yang-Mills, we have various fields as well. We have 6 scalars, which carry an SU4 flavor symmetry. There's fermions, and then because it's a Yang-Mills theory, then we have the gauge field strength F mu nu. And these are all in the adjoint of SUN. And we're not interested in these by themselves. In a conformal field theory, we're interested in gauge invariant operators of them. So multi-traces of products, of derivatives of these things. So I just gave a couple of examples here. You could take a scalar to the power p and take the trace. Or you could take 2 scalars, contract them, add some derivatives. So this is a nice one because this is the stress energy tensor. And the point is that all of these different operators are supposed to match up with the different states on AdS times S, and matching them up, of course, is not an easy task. But here's an example. I could take a graviton in 10 dimensions. I could consider reducing it to the graviton in AdS space in 5 dimensions. Of course, there are other fields. There are, the indices mu nu are not the same as these mu nu, so there are other possibilities here. But let me just focus on the AdS graviton. The AdS graviton itself needs to be expanded around S5. Anyway, so the first term in the expansion would correspond to T mu nu, and the second term would correspond to a kind of a version of T mu nu with an index. And all of these sit within the primaries that we come to call O2 and O3. So actually, in actual fact, all of this mess, at least on the n equals 4 Young-Mills side, all of the mess of supergravity can, in the end, you can sort of just end up focusing on operators which I'm going to call OP. Just take scalar, multiply them together, and then consider various actions of the superconformal group on that. Okay, so that's OP. These are called single trace operators. They're half BPS, and it's correlation functions of these that we're going to be interested in, and it's correlation functions of these which are dual to the whole of supergravity on the AdS side. Okay, so this is the usual story, and it's very complicated. Then we want to try and build up an effective action for 2B string theory, really. And we can now do that. You might want to do that around flat space, but using this holography, we can try and do that or compare with the results when we build an effective action around AdS5 cross S5 space. But in general, it's known that the form of this effective action, so this is a string theory action. It's the effective action where you only involve the supergravity fields, but you've integrated out the string fields. So you have the supergravity, which we know is a bit of a mess. Then you have alpha prime cubed corrections, which have a term which is the Riemann tensor to the power 4 in a certain way of contracting the indices, plus a lot of other stuff. And then at alpha prime to the 5, you can have derivatives, 4 derivatives on alpha prime to the 4. Okay, so a question one could ask is can we factor out the supersymmetry and use superspace in a nice way here? And on the CFT side, can we combine everything in a 10D covariant way? And the answer seems to be yes, at least as far as the tree level 4-point string corrections is concerned. Okay, so let me try and tell you a bit about how this works. Okay, so this is just a brief summary of what I've tried to just say. So we're ultimately interested in these 4-point functions, 4-point functions of OP, OQ, OROS, for any PQRS. And these are supposed to be dual to the 4-point graviton amplitude plus supersymmetric partners. So how does the 10D structure appear in the correlators? So I've already said this really, but at tree level supergravity, there's an answer to this question, and there's a 10D conformal symmetry. And that obviously sort of inspired us to look for this sort of 10D symmetry a bit. But actually the answer we give is slightly different, and it's a slightly different answer for the alpha prime corrections. So just to be clear then, I'm focusing on tree level string corrections. So order 1 over n squared, and kind of all orders, well, I mean, order by order, if you like, in 1 over root lambda in alpha prime. And this is how we want to proceed. So we know what the 4-point string amplitude is on flat space. It's given by the Virasoro-Shapiro amplitude. Okay, so explicitly it's written down here. Okay, as a historical point, the Virasoro-Shapiro amplitude was found by Virasoro for the bosonic string, and it includes tachyons, but it's essentially the same formula appears in the 2B supergravity case, and I think that was written down for the first time in Green-Schwarz-Witten, actually. And Shapiro, I believe, only does higher points, so in this context, it shouldn't really be called Virasoro-Shapiro, but anyway, people seem to call it that. Now, what do I mean by this? So I said that there's a prefactor, there's a kinematic prefactor in front of what I've called AVS here, and a nice way of dealing with that, which I think has only sort of come out quite recently by the work of Green and Wen. Although I think Sonko was there, so he can correct me if I'm wrong. But it is to use sort of spinor helicity techniques that are common in actually in n=4 super-Yang-Mills flat space amplitudes, but in 10 dimensions, and to factor out a delta 16q, and then the a hat is this AVS appearing here. Okay, anyway, that's going to, just bear in mind there's a delta 16q there. It doesn't really matter too much what it is, but it's a Grassmann degree 16 object in some superspace. Right. So let's expand out Virasoro-Shapiro. I mean, we've got gamma functions. We know how to expand them out. We have to use this s plus t plus u equals 0 in order to get it into this form. But we see that the expansion has the form 1 over STU, and then it has some sort of basically a constant, and then s squared plus t squared plus u squared, and so on and so forth, the string corrections. So if we ignore the supergravity term, we could view this amplitude as having arisen from some scalar theory with 4-point interactions. And that's precisely what we're going to do. So we ignore the 1 over STU, and then we view an effective action which would produce this amplitude. So in particular, the term 2z to 3 alpha prime over 4 cubed would arise from just a straight phi to the 4 term with the same prefactor 2z to 3 alpha prime over 4 cubed. Whereas the next term, this s squared plus t squared plus u squared, I would think of as arising from a term with 4 derivatives like that. Okay, so continuing in that way, I can deduce, if you like, an effective action which would reproduce the Virasoro-Shapiro amplitude. This is an effective action in flat space. And one could think of doing that without sort of understanding really what you're doing, which is partially maybe what we did in the first place. But what this is really is it's a prepotential. So as I mentioned, 2B supergravity linearized around flat space is given by a chiral superfield. And so this effective action should be thought of in that way. So it's a chiral superpotential that would appear in an action along with a d16 theta. Okay, so it's a piece of a full effective action, if you like. Okay, so once we've done that, that seems fairly secure in flat space. So now let's think about uplifting this directly to AdS5xS5. So basically, all I want to do is replace my partial derivatives with covariant derivatives. Now, that might make sense if I only had a scalar field theory, but of course I have this big 2B supergravities. There's no guarantee that this is a sensible thing to do. There are some hints that it might be. And the first is that actually, as I briefly mentioned, one can still describe the whole of supergravity linearized on an AdS5xS5 background in terms of a single chiral superfield. Now, some sort of negative result in this direction is that, in fact, the R to the 4 correction to supergravity was originally thought that the full nonlinear theory could actually be written in this sort of way as a chiral action. But then it was realized that that's not actually the case. It cannot be done. And the point is simply that in order to do that, you need to, if you lift, when you lift a theory from flat space to gravity, you introduce a root G, amongst other things. And you, as well as covariantizing your derivatives, you introduce a root G. Now, if we're doing this in a superspace context, you need a root G, which is chiral and preserves supersymmetry. So you need something called delta x of theta, which begins with root G, but has a theta expansion in such a way that preserves SUSY. And it's easy to see, you can do this by matching the theta, the d-body theta SUSYs, if you like, the Q SUSYs. Because it's chiral, you can just use that to actually determine the expansion. But the Q bar SUSYs then have to be automatically satisfied, and they turn out not to be. So that's to do with the full nonlinear theory. So there's no superpotential for the full nonlinear theory. But then Red-German in 2005 sort of pursued this a bit further, and he found that actually the full nonlinear theory, if you're only interested in terms containing R and F5, can be written in this way. So anyhow, none of this is proving anything, but it's just sort of various interesting statements around the subject area. What I would probably say is turn it all around, and what I'm showing you now strongly suggests that there does exist a superpotential for 2V on AdS5xS5. So at the moment, we're just going to assume it and see what happens, and it seems to reproduce the right results. So we'll take that as strong evidence that that it is the case. Paul, okay, so Paul, yep.
Can I make a comment?
Please.
So first, the historical comment is that this Virasoro-Shapiro amplitude, of course, it's not Green-Schwarz-Witten, it's Green-Schwarz, possibly Brink. There was a paper by Green-Schwarz-Brink, I think in '82, where they computed even one loop correction to that amplitude. And
okay.
Tree level is probably in Schwartz review physics reports in '82.
Oh, that's good. I did look for that. I mean, I looked for the reference in the book as well and couldn't find it. So thank you.
Yes, and then, in fact, in '86, Gross and Witten, they reconstructed R4 term from that same amplitude, and they certainly refer to Schwartz and Green, I think. Anyway, but the point, the comment which I had in mind is about the formulas they used is light cone superfields.
Mm-hmm.
They start with Green-Schwarz construction in light cone gauge.
Mm-hmm.
So if you use light cone, then presumably you can have light cone supersymmetry fine at this level. So there's no problem with supersymmetry, I think, at R4. So it's probably demanding full supersymmetry that causes some tension.
Right.
But in AdS, I'm not sure you will need to fix some kind of light cone gauge, analog of light cone gauge, or.
So I think around flat space it's fine. If you're expanding around flat space, there's no problem.
Yeah.
What I was referring to then was sort of the full nonlinear theory.
Yeah.
And then what I'm suggesting is, so I was just mentioning some things about the full nonlinear theory. I'm not really pulling any conclusions from it. Okay. But I'm sort of saying that it seems like there should be such a thing around AdS5xS5.
Okay, sorry. Yeah, it was just going.
Okay, no, thanks.
Sorry, can I also comment on another thing? So you have like for supergravity only, you have a term 1 over STU.
Yes.
How is it compatible with like standard expectation from like analytic structure of amplitudes? I mean, like you have a double pole or triple pole.
Oh, well, yeah, that's to do with the prefactor, I think, removes that for any particular, for any specific component amplitude you compute, that will be removed.
Oh, okay. Thank you.
Okay. Good. Okay, so the idea is that I just lift now. I lift this effective superpotential here into AdS cross S. Okay, so I lift it. Of course, when I lift a flat space
Can I ask a question?
action, yep.
Why do you call it superpotential? While it looks like it's just a normal potential, like a scalar potential.
Well, it's a chiral. I mean, it's I have to integrate against d16 theta. I don't know. But anyway, this is what it is. Whatever you want to call it.
Okay. No, I thought there was some more deep, please. Yeah. Okay, because there is also theta.
There's d16 theta, yeah.
Okay, thanks.
And that's why, by the way, so this produces r to the 4. So you can, how does it produce r to the 4? When I input phi to the 4. And that's clear, right? Because r comes from theta to the 4. And so I give 4 thetas to each, or 4 d's to each phi, and then I get r to the 4 out.
Okay, thanks.
Okay, so I lift this up. It's not unique for 2 reasons. Okay, I can never uniquely lift a flat space action to curved space. So phi to the 4 I can lift almost uniquely. But if I've got derivatives, then there are ambiguities due to the fact that covariant derivatives no longer commute. So many different ways of orienting covariant derivatives produce the same action in flat space. And then here there's another problem, if you like, or another ambiguity in that you can have alpha prime over r squared corrections. This is a dimensionless quantity now, because I've got a new scale in the game, the radius. And so this is the uplift, if you can see it. So I've got phi to the 4 term, and the first part of that is fixed by Virasoro-Shapiro, but then there's an expansion in alpha prime over r squared, and these 2 constants are not fixed. Then I can go to alpha prime to the 5, and again the first term is fixed in b. So this is nabla phi dot nabla phi squared, which is the analog then of this. So that term just lifts, but then there are other terms like this one. This would be 0 in flat space because nabla squared would commute through nabla mu and hit phi, and that's 0 by the equations of motion. Okay, so I lift it up and I get various terms. Okay, so that's what I do. And now the question is, how do I extract correlators from this? So now I define a very specific, if you like, you could call it a generating function of correlators. So first of all, briefly review the scalars again. So I'm introducing these y coordinates, 6 y coordinates to contract the SO6 index. And then I'm also going to use a particular normalization of my operators, which is inspired by the work of Karen Huot. So there's a 1 over p in the normalization of the 2-point function. Okay, now the y's, you'll notice, look very similar to the x's. There are 6 of them. They dot to 0, but now in a Euclidean metric. And also on the S5 and AdS5 side, I'm going to have y hats and x hats bulk fields, bulk analogs. the analogy between y and y hat is exactly the same as that between x and x hat. So, you know, y hat dot y hat is equal to 1, just as x hat dot x hat was equal to -1. Now, in n equals 4 super-Young-Mills, there are superconformal ward identities and non-renormalization theorems that tell us that any half BPS operator has this form. It's given by the free theory, which is somehow separate. Then there's this polynomial, sort of simple polynomial in x and y's, and then there's the function itself, a function of x and y. So all operators have this form. So it actually makes a lot of sense to discuss this quantity and call it the interacting part of the correlator. So I just take that over to the left-hand side and divide by I. And I really, you should think of as playing the same role as delta 16q or integral d16 theta. Actually, this was pointed out by Green and Wen. And now what I want to do, as well as define this interacting part of the correlator, I want to package them all together into one object like this. Now, let's just think a little bit about that. So every term in PQRS has a certain weight in the y's. So by adding, we don't normally think of adding the correlators together because they have different weights in y's, but that's actually a very natural thing to do if you're trying to extend it to, you know, if you want to relate it to some AdS5 times S5 action, you're not going to have homogeneity in the y's. So so we add them together like this, and it's this object that we're going to compare directly to calculations in AdS5 cross S5 in a second. Let me just say one thing before I go on about the weights, which is quite interesting. So O2 has dimension 2, and it has a non-trivial SU4 rep. That's just a fancy way of saying that it has an OIJ indices. Now, this I actually removes the SU4 charge and increases delta. So this looks like a correlator of operators which are dimension 4 and are SU4 singlets. And that kind of matches on to the fact that we're going to be comparing it with massless 10D scalars, which in flat space have delta equals 4 and are obviously SU4 singlets. Okay, so as I said, we're going to obtain this object from a 10D bulk computation. So let's just see how to do that. So this is the final kind of new ingredient, if you like, is to extend my concept of a Witten diagram to an AdS times S Witten diagram. Okay, so this slide is, if you've got a short memory, that's what I told you a few moments ago. There's a bulk to boundary propagator, and these are the D functions. Now, given this analogy between X and Y, it makes a lot of sense to consider a similar object for the S5. So again, this is a standard D function, but now I can write what we call a B function, and well, it's basically the same formula except that you've got the objects in the numerator instead of the denominator. And this actually follows from some work of Chen and Sakamoto, who were looking at similar things and introduced this bulk to boundary propagator on the S5. But then we do something even more. We now consider this 10-dimensional bulk to boundary propagator where you combine the two together. So you combine the x hat dot x plus y hat dot y. So if I expanded this out in the y's, I would get a sum of increasing powers of x hat dot x and y hat dot y. So I'd kind of get a sum of terms of both of these. But this form is nice because it satisfies the massless equation of motion. So 10D nabla squared which splits into an AdS5 plus an S5 nabla squared, acting on this G, gives 0 kind of non-trivially when delta is equal to D. Delta equals D is what we're going to have. We're going to have D equals 4. Sorry, D I never really defined probably, but D is the space-time dimension, which has to be equal to, so we're talking about AdS D plus 1 times SD plus 1, basically. Almost everything I say applies to that case. So D is 4 is the interesting one for us at the moment. Okay, and then I define an AdS times S generalization of a Witten diagram. I simply write the same thing down. Now I integrate over X hat and Y hat, and I integrate these sort of generalized bulk to boundary propagators that have, so I've just defined P and Q to be these. So that's basically this propagator inserted in there. Okay, so that's what we call an AdS times S Witten diagram, and that's what we want to then basically use. So if you give me an effective action in 10 dimensions on AdS5 because S5, I basically want to use these bulk to boundary propagators and extract correlators from that. So firstly, as I just mentioned, you can easily expand the propagator. If you don't like the 10-dimensional structure, you can easily get back the AdS5 times S5 structure by expanding it out in this way. So here it is, explicitly expanded out. This AdS5 plus S5 Witten diagram, if you like, contact Witten diagram, is the following sum of ordinary contact Witten diagrams and the corresponding sphere ones. Okay, and we can easily convert the whole thing to Melon space as well. And then the relation to correlators is really just that. I just relate that correlator that I just defined, 0,0,0,0, and that is supposed to be then equal to the result of taking my effective action and replacing phi with G. So here's an example. We take the alpha prime cubed one. So that's an integral over 10 dimensions of phi to the 4. And now I just replace my phi's with the G. So P1 plus Q1 to the 4, P2 plus Q2 to the 4, and so on. And that then gives me, well, I mean, it gives me what it gives me, but it reproduces what people have found via various bootstrap techniques. Okay, so the expansion in Y, first of all, it gives me all the correlators OPQRS. You can just expand them. It's just the formula I gave you before. And let me just go back. It's just this formula, just in a special case when all the delta i's are 4. So that's that sum. And then you picking out any particular term then gives me the correlator OPOQOROS.
Well, I think I missed, you mentioned 12-dimensional. Did you mention conformal symmetry?
No, well, not really. I'm trying not to.
Okay. All right. Okay.
I'll maybe get onto that, but not in 12 dimensions, no. I mean, I'm sort of in 12 dimensions because I've got 2 embedding spaces, but yeah, but I don't think I want to see that as really meaning anything. Anyway, this gives the correct result. So this was found. The result was found by these people. Oh, actually, it was we compare it in Melon space in the end, not in this X space. But anyway, all we need to know is it gives the right result. So let me just do one further example, alpha prime to the phi. So what does that look like? So I saw that we lifted the Virasoro amplitude to a superpotential in AdS5 because S5, and this term is then fixed. This term we call main, And then there are two ambiguities. One came from expanding out the phi to the 4, and one is a sort of a genuine new term. And then the idea is, okay, I've got nablify, nablify. It's just covariant derivatives acting on this G. So I can compute what they are. It turns out to be that sort of thing for the main one. And then again, I can expand in the Y's as before and obtain expressions for all the correlators in terms of D functions and B functions. And that also gives the same results that were found by these people. And the same two ambiguities, interestingly. These ambiguities were also fixed earlier by localization in n equals 4 Yang-Mills. So we can't say anything from this point of view about these ambiguities, they're just ambiguities. But then we can now say that we have precisely fixed the effective action in AdS5xS5 using these results from localization n equals 4 Yang-Mills. Okay, so you can now go further. So what's the technical issue here? So there's a couple of technical issues. First of all, is doing the covariant derivatives. It becomes tedious. And there's a computer algorithm we sort of developed for doing that. And the second point is actually, how do we want to display the answers? And it's more convenient to display them as Melon amplitudes than in the way here I've just displayed them like that. I mean, okay, that's an answer if you like, but and you can expand it out, but it's nicer to use Melon amplitudes. So I want to I'll probably skip this bit because of time, but there's a way of implementing covariant derivatives, and oops. And then there's Melon amplitudes. We can talk about Melon amplitudes. We define sort of AdS times S Melon amplitudes, if you like. And also, there's an explicit expansion of these B functions. So this is just an explicit expansion, really. This is just you say, okay, I have this B function, which is an integral over S5. What is it? So it's a function of yi and y. It's a function of yi, sorry. So in the end, it's going to be a function of yi dot yj, and this is the function just explicitly written out. And you can do that. The only real integral you have to do is the integral over the 5 sphere. So you get the volume of the 5 sphere, and the rest is combinatorics. But interestingly, it sort of looks like the Melon amplitude, except that there's a sum instead of an integral. But you know, you've got this sum of dij is pj, and whether it was sum of delta ij is delta j, and so on. Okay, and then we can define AdS times S Witten diagrams just by putting it all together. The formulae start to get a bit lengthy, but that's just because the number of ingredients in them, really. They're remarkably simple. So this is the Melon amplitude, and for example, the Melon amplitude of alpha prime cubed then is just sigma p plus 3. It's just essentially this term in the specific case that we're looking at. And actually, it was this. So this is a Pochhammer, by the way. Sigma p plus 3 times sigma p plus 4 times sigma p plus 5, where p is the half the sum of the pi's of the particular correlator we're looking at. Okay, and it was that form that kind of inspired us really to ask what it looks so close to being a D function. You know, how can we interpret it like that? And just to say, okay, the details are not important, but any derivative contact interaction. So there's an algorithm for working it out that I've skipped. But in the end, it's going to come to be a polynomial of terms of this form. So this is a very general formula, but it's basically just the bulk to boundary propagators on the bottom, and then polynomial, an arbitrary polynomial in the top. And any term of this form maps to a Melon amplitude, and the mapping is linear. So any polynomial, I just map it to this Melon amplitude. So to summarize, there's a very straightforward algorithm for taking any phi to the 4 interaction with any derivatives, an algorithm for applying the derivatives. It gives a sum of terms of the above form, and then I just convert it to the Melon amplitude. And here's the alpha prime to the 5 Melon amplitude written in a certain way. It's again, it's quadratic in the variables. Now I have STU variables on AdS5 and similar variables on S5. And this form was actually found earlier by these people, by bootstrap techniques. Okay, so here's where the interaction comes in. So a lot of these results have been found by sort of intricate bootstrap. You write an ansatz for the Melon amplitude, an ansatz for the form of anomalous dimensions, and sort of look at how they mesh together with the flat space limit. And if you do that, you end up with some ambiguity, some things that can't be fixed by looking at the flat space limit. And so here we sort of have an interpretation of those. Okay, how are we doing? We're kind of out of time. So okay, you can do higher order corrections. Alpha prime 6 and alpha prime 7 we did explicitly. So someone mentioned conformal symmetry, and I don't really have much to say about that. So, but the following is what I do have to say about it. So maybe I'll just quickly discuss that. So this is supergravity. So I've explicitly excluded supergravity from what I've been talking about. That was the 1 over STU. But you can think that given that that was where the 10D conformal symmetry originally was found, it seems strange to then exclude it from the story. So I just want to quickly look at that. So this is what, in the way that I've been writing things, this is what supergravity looks like. And it's just, this is again combined in this 10-dimensional form. So that's the full, all the correlators put together in one go, written in terms of this D2422. And the Melon amplitude has this simple form, which again is reminiscent of 1 over STU. So what I would like, okay, this is just speculation really. I'd like to view this somehow as some inverse derivatives acting on a phi to the 4 interaction. So I'd like to stick it in my superpotential, but in the form of inverse derivatives. Yeah, I don't know if there's it seems natural also from the point of view of Virasoro-Shapiro, if one wanted to kind of have a summed up formula in any way, the Virasoro-Shapiro had 1 over STU times gammas. So it sort of makes sense to try and mimic that a little bit. And that's a potential way of mimicking that. But the 10D conformal symmetry comes about from this point of view. So these AdS contact diagrams that I introduced are kind of quite closely related to the standard flat space contact diagrams. And a way of relating them, and you can see this by looking at the corresponding Melon forms. The way to relate them is basically to rescale the y's with R and rescale the whole thing with a certain way with R, and then differentiate with respect to R a certain number of times, and then rescale back again. Okay, and then I can take any of these AdS5xS5 contacts and write it as a flat space one. But in particular, if sigma delta equals D over 2 plus 1, then all of these rescalings disappear. Okay, I don't need to rescale if I have sigma delta equals, sorry, I think I mean D plus 1. I think I mean D plus 1 there. So then this disappears. Okay, and in particular for supergravity, we have D2422. And lo and behold, if I take sigma delta for 2422, I get 5, which is equal to D plus 1, because D is 4. So supergravity is, you know, I want to, what am I trying to say here? I'm just trying to say that supergravity has a special, when written, so, okay, first of all, I can write the supergravity answer in this manifestly 10D form. And if I do that, it does have a special property that the AdS5xS5 contact term is equal to the flat space contact term. And that for me is where the conformal symmetry comes from. But on the other hand, it doesn't really naturally combine unless you're happy to discuss these inverse derivatives. And it shouldn't really combine, sorry, I missed this point, because it contains 3-point interactions. The whole point of what I've been doing is that the alpha prime cubed and so on, they start with 4-point interactions, r to the 4, and therefore there's a natural map to 4-point amplitudes, whereas supergravity starts with 3-point amplitudes. Okay, good. Well, there's a sort of a summary of the status of things in terms of loop corrections and alpha prime corrections. I can talk about that if anyone wants to ask me about it. There's different. Oh, and also since I think Sonkar is here, I should mention this, that the extend this sort of effective action where I had coefficients which were zetas, but actually these can be extended to full Eisenstein series functions, and then that then gives you even more information about further correlators, further perturbative ones and non-perturbative instanton corrections as well. And then of course there's loop corrections, which I couldn't, you know, people have worked out supergravity loops and even string loops more recently. Okay, so that's what I wanted to say really. Things to do. Well, again, as is probably clear, I'm saying that this is implying that there's a scalar superpotential in AdS5xS5. So obviously it'd be nice to look at that kind of directly from the AdS5 point of view, rather than using bootstrap results to deduce it, if you see what I mean. Also, the results that we get, we're expanding higher and higher in alpha prime still, so it'd be great to actually, you know, spot a pattern or whatever and find the full Virasoro amplitude on AdS5xS5. So we have a mechanism for computing it, but maybe it can be written in a nice way in terms of gammas, just as the flat space version is. Higher points. So Green and Wen recently wrote about the maximally nilpotent correlators. They should be quite amenable because there's still a SUSY factor that's pulled out. Now, right at the start, I pulled out this factor, this IXY factor. So if I go to 5 points or higher points, non-maximally nilpotent, then I think it's not so clear what correlator I should compare to, because I don't really know how to factor out supersymmetry. I can't factor it out in a unique way. Other backgrounds don't seem immediately clear how to apply this, but there are lots of things that are nice and simple for AdS5xS5 that become more complicated for M theory in terms of the blocks and this factorized form and so on and so forth. So it's not impossible that one can do something, but one has to be a bit more clever. Whereas things like AdS3 times S3 and AdS2 times S2, they should be okay. And yeah, I mean, loop corrections. Did I say loop corrections somewhere? It'd be nice to see if one could use this to do something with loop corrections. But again, one needs to understand the supergravity part better before that would be possible. Okay, thank you very much.
Thank you.
Sorry, I went over.
Are there any questions?
So what would happen if instead of concentrating on this superpotential, we just look at, say, dilaton in 10 dimensions and try to, so for the dilaton, for the scattering of dilaton, you have the same Virasoro-Shapiro amplitude. and you can reconstruct the action for that. That will be very complicated. Well, you'll have more covariant derivatives of it, right? So that would be the complication.
Yeah, no, I think you're right. I think what you're basically saying is so there's two aspects to this, I guess. There's one is that supersymmetry factors out in a nice way. And then the whole problem essentially just becomes an AdS5 times S5 problem, or if you like, in terms of group theory, an SO6 times SO4, 2 problem, rather than a SU2, 2/4. You know, it's just the bosonic part. And so these Witten diagrams, these generalized Witten diagrams would, you know, so you could imagine just a scalar in AdS5 times S5, so the dilaton, for example, and then I think you could use these techniques indeed. So, but how, I mean, I guess the point here was really sort of comparing to some results from the half BPS operators. So if you wanted to find the corresponding components that corresponded to the dilaton, then you could do that.
Yeah, so that will be just next term in the supermultiplet, sort of, because yeah, dilaton starts with dimension 4, so you'll have
yeah, it would be the Lagrangian, right?
Yeah, it's Lagrangian. Yeah. Okay, thanks.
Can you comment a bit more like on the conformal symmetry? I'm not sure that I understood. So are you saying that supergravity in 10D is conformally invariant in the sense like, I don't know, SO 10,2? Or...
SO 10,2, right, yeah. Well, yeah. I'm not saying that. Azimon, Karen Hewitt, and Trin said that. So the supergravity indeed has this apparent conformal symmetry.
Yeah, I'm asking because there are not that many conformal fields, especially like in 10D. So you have scalars, fermion, and other fields are of mixed symmetry, and they have like 5 rows.
But that's not. It's not the symmetry of the supergravity. It's a particular symmetry of some correlators. It's acting just on these correlators. I'm not sure you can.
Yeah, it's a funny thing. It's there for the correlators corresponding to tree level supergravity. So I mean, well, it depends how you interpret things. But then it's there for the free theory as well, in some sense. But you actually need to kind of look at slightly different correlators. There's this funny differential operator delta 8, which takes you actually from the Lagrangian multiplet we were just talking about to the highest weighted state. And in the free theory, you look at L bar, and it has this conformal symmetry. And then in the tree at tree level, you then look at O2, 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 and the higher ones from there. You look at the primaries, sorry. So it's a very funny thing. It's not like you have the whole theory doesn't have it, but as Arkady was saying, it's just seems to be some sector on the n=4 side. And what that means on the supergravity side, I don't really know.
Sorry, can I make a comment about this point?
Sure.
So actually, this Hillen conformal symmetry is not a property of supergravity. It has more to do with the conformal flatness of the background. So actually, this Hillen conformal, yes. So this structure actually is also present for just spin 1 super gauge series in AdS. So in a paper that will come out next week, actually, we're going to discuss these for the n=2 SDFTs coming from these 3 branes probing F-series singularities. There you can find that the super gluon amplitudes on AdS5 times S3 also has this Hillen conformal symmetry, but it's 8-dimensional. So it has nothing to do with supergravity.
Okay, that sounds interesting. Yeah, all I was saying is that, so we found this 10D symmetry, but not conformal. So we're packaging everything together in a 10D way. And I was kind of observing that, where was it? I lost, here we go. I was just observing the fact that in the gravity case where we do know that we have conformal symmetry, we do also have this coincidence that a general mapping from AdS5xS contact diagrams to flat space contact diagrams is direct. I have a general mapping, but it involves this d/Rs and rescaling and so on and so forth. Whereas in the case that we have supergravity, that there's just a direct mapping. So in this case, again, it looks a bit like a sort of a coincidence, you might say, for when these deltas satisfy a certain equation, namely this sigma delta equals d plus 1. That's the sort of what I was trying to say. However, you can say a bit more. You can actually talk about the conformal symmetry of the alpha prime cubed corrections as well. But you have to apply a big differential operator to it to see the conformal symmetry. Again, maybe it's I guess, well, I don't know how to make it precise, but it feels like it's the analog of this d/R here. So I do something to my correlator, and then actually, sorry, it's the other way around. I take a seed correlator that has conformal symmetry, and then I do something to it to produce the correlator that I'm actually interested in. By do something, I mean apply a large differential operator to it. But that breaks down for alpha prime, even that breaks down for alpha prime to the 5. And that's related to, I guess it's related to the fact that I have these covariant derivatives, which are just spoiling any, any conformal symmetry that's left is somehow spoiled because of the covariant derivatives.
Okay, thank you. Any more questions? Okay, then thank you very much for a nice talk. And
thank you very much.
Yeah, thank you, the audience, for coming. And yeah, goodbye. See you next time.
Okay, thanks. Bye.